Another example of being able to use or to find the interval of convergence for a power series. So we have n squared x plus 1 to the 2n divided by n factorial. Now, this one's a little bit different than any of the ones that we've seen before, because I want you to notice that we have a couple terms, or a couple factors at least, the n squared and the n factorial, that are not raised to the nth power, okay? So what this means for this one is we have to use the ratio test to be able to determine the interval and radius of convergence, right? So remember, ratio test says that we're going to take the limit as n approaches infinity of a sub n plus 1 absolute divided by a sub n. And if that's equal to some real value L, and L is less than 1, then it converges. Okay, so that's the condition for convergence. All right, so what we're going to do at this point is we're just going to employ the ratio test. All right, so now this is going to be a little bit difficult to write out, so bear with me. So lim as n approaches infinity. All right, so we're going to go ahead and just put in n plus 1 for every n. So n plus 1 squared, and then x plus 1 to the 2n plus 1. And then we're going to divide that by n plus 1 factorial. And then we're going to divide all of that by the original sequence, the n squared, and then x plus 1 to the 2n, and we're going to divide that by n factorial. All right, now, and that has to be less than 1 for it to be convergent. Now, remember the trick that we use. We have to multiply by the reciprocal of the denominator, and then we're going to go ahead and just try to multiply or try to group up the like-looking sort of factors. Okay, so this is going to be the limit as n approaches infinity of the absolute value of n plus 1 squared, x plus 1 to the 2n plus 2 divided by n plus 1 factorial. And now we're going to multiply by the reciprocal of the denominator, which is going to be n factorial divided by x plus 1 to the 2n and then n squared. And that has to be less than 1. Now, what I'm going to do is I'm going to group like-looking factors, and things that look alike are factorials, x's, and then the n squareds. Okay, so or the n plus 1 squared. Okay, so let's write this as 3 different sort of little fractions that are multiplied together. And so that's going to be the limit as n approaches infinity of, so let's start with the factorial, n factorial over n plus 1 factorial. And then we have the n squareds. That's going to be n plus 1 squared divided by n squared. And then finally, we're going to have the x to the n plus 1s. So we have x plus 1. I'm sorry, we're going to have x plus 1. And then to the n's, so that's 2n plus 2 divided by x plus 1 to the 2n. All right, and for that to be convergent, it has to be less than 1, just able to squeeze it in. Now, let's simplify each of these. All right, so some good news is that if I wanted to, I could just go ahead and simplify this whole thing by using the definition of the factorial. So remember, we have n minus 1, n minus 2, all the way down to 3, 2, 1. And then in the denominator, we're going to have n plus 1 times n minus 1 times n minus 2, all the way down to 3, 2, 1. All right. And so everything's going to cancel out, and we're just going to be left with a denominator of n plus 1. All right. So the next line, we're going to have lim as n approaches infinity of 1 over n plus 1 inside the absolute values. All right. So this is going to be n approaches infinity of the absolute value of 1 over n plus 1. I'm going to keep the n plus 1 square over n square momentarily. So this is going to be n plus 1 squared over n squared. And then over here, notice that we have 2 of these, all right? And then in the numerator, 2 to the 2n plus 2. So we could break off 2 of these. We could rewrite this expression as x plus 1 squared, x plus 1 to the 2n divided by x plus 1 to the 2n. Notice those would cancel out, and we're left with x plus 1 squared. Right? And by the way, you could just go ahead and skip immediately to that step by just canceling those out and seeing that you only have 2 left. All right. But I just wanted to make sure for those of you that haven't necessarily worked with the exponentials to this degree that you can see how to do it discretely. All right. Notice that we have an n plus 1 squared and n plus 1. So we cancel these out. And we're going to be left with the limit as n approaches infinity of the absolute value of n plus 1 divided by n squared times x plus 1 squared. All right. Now, we still have to take the limit of this animal. All right. And it's actually pretty easy to do so because we can just break it up into 2 separate smaller fractions because we're dividing by a monomial. So we have the limit as n approaches infinity of n over n squared plus 1 over n squared. And then we have that x plus 1 squared. Right? This is going to simplify clearly into 1 over n. Right, so we could just rewrite that immediately as 1 over n just by dividing it out. And now if we employ the limit to both of these, well, that just becomes 0 plus 0. Okay, so now we get the absolute value of 0 plus 0, x plus 1 squared less than 1. Okay? Or by some significant computation, that's going to be 0 times x plus 1 squared less than 1. Now, this is going to say, remember, the question is, what values of x can we plug in to make this true? And notice that no matter what values of x we plug in and square it, so if we plugged in 3 million, we get 3,000,001 squared times 0, okay? So what we know is that this series is going to converge for all values of x, okay? So this statement is valid for all values of x. Okay, and so if that's true, because no matter what number we plug in, okay, if that's true, that means that the interval of convergence is going to be from negative infinity to positive infinity, and the radius of convergence is going to be infinity. All right, that only works if you eventually get to multiply all the x values by 0. Okay, so hopefully that wasn't too bad using the ratio test. Okay, so notice using the ratio test is a little bit uglier, okay, because of the significantly more difficult algebra involved. Okay, but we've seen it in previous sections, so we know the techniques necessary to be able to do it successfully. All right, so we have a few more examples in subsequent videos, and we're eventually going to get to the point where we use the ratio test and we have to check the endpoints. Okay, so we're going to see those in, I think, our next couple videos.